For over a century, physicists have been intrigued by the idea of black holes, with the concept gaining traction around 1916. These cosmic anomalies are among the most captivating and enigmatic phenomena we know, sitting at the intersection of vast gravitational forces and a peculiar invisibility to our understanding. A black hole, potentially weighing as much as 2 to 4 million times the mass of our Sun, remains a mysterious presence in the cosmos. Despite decades of intense research, our understanding has expanded from almost no knowledge to piecing together more details, with even more discoveries being made recently. A breakthrough by Michio Kaku has revealed startling insights about the interior of black holes, which may challenge our long-held assumptions and offer new perspectives on the nature of these celestial bodies. This new information opens doors to deeper explorations into what might have been overlooked until now. Join us as we venture further into the fascinating world of black holes and uncover what's hidden within the universe's vast and inspiring expanse. But what exactly are black holes? Before we delve into the latest findings by Michio Kaku, it's essential to revisit the basic understanding of black holes. While the black hole mystery is familiar, most of us have only a general sense of what a black hole is, and there are still key elements that remain unclear. In 1916, Albert Einstein's groundbreaking theory of general relativity predicted the existence of black holes. At that time, the notion was purely theoretical. It wasn't until about 50 years later that evidence was discovered confirming that black holes are real objects in space. This revelation came in the 1960s during studies of the star X1, a luminous celestial body emitting X-rays. Observations showed that these X-rays were not just randomly moving, but were being drawn into a dense, invisible mass. This mass, later identified as a black hole, changed our perception of the cosmos. The discovery was monumental, as it proved that black holes were not figments of Einstein's imagination, but tangible, elusive entities that warranted further investigation. Following this groundbreaking discovery, scientists worldwide began a global quest to uncover more about black holes. Their efforts led to the realization that the Milky Way alone may host around 100 million black holes, though, due to the challenges in detecting them, this estimate remains imprecise. Even though black holes are incredibly difficult to pinpoint, scientists believe that millions of these massive entities are hidden within our galaxy, making it even more crucial to understand them. Let's break down the core concept of gravity. Black holes exert such immense gravitational forces that anything entering their domain is squeezed into a singularity, a point where the laws of physics, as we know them, cease to function. In simpler terms, black holes are like gigantic vacuum cleaners, pulling everything into them. One of the most terrifying aspects of studying black holes is that if someone were to fall into one, they would gradually stretch out and become a singularity, their body torn apart by the intense gravitational forces before the point of total destruction. It's best to avoid getting too close to one, though they are scattered across the universe. Despite the nearest black hole being nearly 500 light-years away, the proximity still raises legitimate concerns. In 2021, scientists achieved a historic milestone by capturing the first clear image of a black hole, the M87 black hole. This achievement was the result of numerous nights spent taking photos and aligning them to create a single cohesive image. As more data was gathered, researchers were able to discern that black holes consist of 3 distinct layers. Contrary to the common misconception that they are just endless voids. 1. The event horizon marks the point beyond which nothing can escape. Once something crosses this boundary, it is inevitably drawn toward the black hole. 2. The photon sphere is where light itself gets trapped, unable to escape due to the powerful gravitational forces at play. 3. The singularity, where all matter is compressed into an infinitely small point, a place where the very fabric of reality collapses and all known laws of physics break down. What's even more intriguing is that each black hole is unique in its own right. While they follow the general 3-layer structure, the way they behave can vary significantly. This makes them particularly challenging to study, as conventional scientific methods don't apply. Scientists have no choice but to investigate these anomalies through indirect means, such as observing the radiation emitted from them or analyzing the gas and dust swirling around them. Sending a probe directly into a black hole is an exercise in futility, as anything that crosses the event horizon is inevitably pulled toward the singularity where it is crushed into nothingness. This unavoidable fate means that billions of dollars cannot be spent on probes that would meet their end before offering any valuable data. Consequently, researchers are left to study black holes in 2 dimensions, despite them being 3-dimensional singularities. Adding to the complexity of black hole research is the fact that no 2 black holes are identical. When studying them, we must account for the breakdown of physics as we know it. Theories about the origins of black holes suggest that they may form when massive stars collapse in on themselves. As a star burns through its fuel, it can no longer produce enough energy to counterbalance the inward pull of gravity, leading to its eventual collapse into a black hole. If the star is massive enough, this process continues until the collapsing matter becomes a singularity. To further understand the nature of black holes, NASA scientists turned their attention to the center of the universe, particularly the M87 galaxy. There, they observed a powerful whirlpool of hydrogen gas spinning at mind-boggling speeds of 1.2 million miles per hour. The centrifugal force should have caused this gas to fly apart, but instead, it remained intact, suggesting the presence of a massive object at the center, likely a black hole. This object is believed to weigh up to 3 billion times the mass of our Sun. Another significant theory was proposed in 1963 by New Zealand mathematician Roy Kerr, who used Einstein's equations to describe the behavior of rotating black holes. He argued that, rather than collapsing into a point as previously thought, a rotating black hole forms a thin ring-like structure known as the ergosphere. This rotating disk of matter is key to understanding the breakdown of physical laws in the vicinity of black holes. Kerr's model also predicted the existence of an Einstein-Rosen bridge, a theoretical wormhole that could provide a shortcut through spacetime, connecting distant regions of the universe or even parallel universes. To grasp the idea of a wormhole, it's important to understand the concept of spacetime as described in Michio Kaku's mind-blowing explanation. Einstein's theory of spacetime is a four-dimensional fabric that is warped by objects with mass. This warping creates gravitational fields that influence the movement of other objects. Think of spacetime as a piece of paper, and if you fold the paper, you create a shortcut between 2 points. This shortcut is the essence of a wormhole, a passage through spacetime that could connect distant locations almost instantaneously. Detect with current instruments. These extra dimensions, according to superstring theory, are compactified, existing on scales much smaller than atoms or even subatomic particles. While the theory remains highly speculative, it offers a fascinating glimpse into how the universe might function at its most fundamental level. Superstring theory could also provide a framework for unifying the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. By doing so, it may eventually help explain how phenomena like black holes and wormholes fit together within the larger structure of the cosmos. As research into black holes and quantum gravity continues, theories about their formation and nature evolve. While the nature of black holes and the possibility of wormholes remain intriguing puzzles, we are still far from fully understanding these cosmic giants. Yet, the discoveries we have made thus far hint at the complexity and wonder that still awaits us. New technologies, such as advanced telescopes and computational models, are constantly improving our ability to study the universe in greater detail. These tools will allow us to probe deeper into the mysteries of black holes, perhaps unlocking even more profound secrets about spacetime, gravity, and the fabric of reality itself. In the years ahead, the study of black holes promises to reveal new insights about the universe, our place within it, and the fundamental laws that govern all matter and energy. As scientists like M. Yakubu continue to explore these celestial enigmas, we can only wonder what other astonishing discoveries lie ahead. One thing is certain: the universe is far more complex and mysterious than we ever imagined, and black holes remain one of its most captivating puzzles. Despite the challenges, the pursuit of understanding black holes, wormholes, and the fabric of spacetime continues to captivate scientists, offering the potential for groundbreaking discoveries that could reshape our understanding of the universe. Continuing from where we left off, the pursuit of superstring theory and other theories that aim to unify the forces of nature is an ongoing challenge, but it holds the promise of unlocking new insights into the very nature of reality itself. These theories propose that the universe is composed of more than the familiar three dimensions of space and one of time. In fact, they suggest that additional dimensions exist, but they are so minuscule and compact that we are unable to observe them directly with current technology. However, their existence could provide the key to understanding phenomena like black holes, wormholes, and the deepest mysteries of the cosmos. Superstring theory offers a fascinating picture of the universe, proposing that all matter and forces are manifestations of tiny vibrating strings. These strings can vibrate at different frequencies, with each vibration corresponding to a different particle, just as a guitar string can produce different musical notes based on how it vibrates. The fundamental particles of nature might correspond to different vibrational patterns of superstrings. If proven, this theory would not only provide a unified explanation for the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, but also open up entirely new ways of understanding the universe's structure. This could potentially provide answers to some of the biggest questions in physics, including the nature of dark matter and dark energy, which together account for a vast majority of the universe's mass and energy but remain largely mysterious. Yet, despite its elegance and promise, superstring theory remains unproven. One of the major hurdles in testing the theory is the fact that the extra dimensions it predicts are so minuscule that they are beyond our current observational capabilities to detect. To detect these dimensions, we would need instruments of unprecedented sensitivity and precision, and even then, the evidence might be indirect. This makes superstring theory a challenging subject to test through traditional scientific methods. Yet, its mathematical beauty and coherence make it one of the most compelling ideas in theoretical physics. At the same time, scientists are also working on other approaches that might lead to breakthroughs in our understanding of black holes. For example, quantum gravity is another field of research that seeks to combine the principles of quantum mechanics, which govern the behavior of subatomic particles, with the theory of general relativity, which explains the behavior of large objects like planets, stars, and black holes. The hope is that by merging these two theories, scientists can gain a clearer understanding of how gravity works on the quantum level and, in turn, gain deeper insights into the nature of black holes and other cosmic phenomena. The intersection of quantum mechanics and general relativity is especially crucial when studying black holes because the extreme conditions near a black hole's event horizon, where gravity is extraordinarily intense, demand a theory that can account for both quantum effects and relativistic effects. In fact, the interior of a black hole, where the singularity exists, is one of the most puzzling and extreme environments in the universe. The singularity represents a point where space and time become so warped that the usual laws of physics break down. Understanding what happens in such a place requires a theory that can reconcile quantum mechanics and general relativity. This has led to the development of ideas like loop quantum gravity and other quantum gravity models, which aim to resolve these contradictions and provide a more complete picture of black holes. As we continue to probe the mysteries of black holes, one thing is certain: the more we learn, the more we realize how much there is still to discover. Black holes are not just points of destruction, but are also places of incredible complexity and potential. Whether they are gateways to other dimensions, as some theorists believe, or whether they hold the key to understanding the deepest secrets of space and time, black holes remain a crucial area of study. As our tools and theories evolve, so too will our understanding of these enigmatic objects. Looking ahead, the next major challenge will be to refine our methods of observing and studying black holes. One of the most exciting advancements in recent years has been the development of gravitational wave astronomy. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as the merging of black holes. By detecting and analyzing these waves, scientists can learn about the behavior of black holes and other celestial objects in ways that were previously impossible. The detection of gravitational waves has already provided groundbreaking insights into the dynamic processes of black hole mergers, and future experiments are likely to yield even more revelations. In addition to gravitational waves, another promising area of research involves the use of advanced telescopes and imaging techniques. The Event Horizon Telescope, EHT, which produced the first image of a black hole in the M87 galaxy, is an example of how innovative technology can shed new light on black holes. By combining data from multiple radio telescopes around the world, the EHT was able to capture an image of the black hole shadow, offering a glimpse into one of the universe's most mysterious phenomena. As technology continues to improve, it's likely that we will be able to observe black holes in even greater detail, revealing more about their structure, behavior, and role in the cosmos. The study of black holes is not just about understanding these strange objects in isolation, it is also about understanding the fundamental workings of the universe. Black holes are crucial to our understanding of space-time, gravity, and the very nature of reality. By studying them, we are not only learning more about these objects themselves but also about the laws that govern the universe at its most extreme scales. In conclusion, the study of black holes is one of the most exciting and challenging fields in modern physics. With each new discovery, we inch closer to unraveling the mysteries of these cosmic giants. Whether through the study of gravitational waves, advancements in imaging technology, or the development of new theories, black holes continue to captivate the imagination of scientists and laypeople alike. As we explore the universe's most extreme and enigmatic objects, we are forced to confront fundamental questions about the nature of spacetime and existence itself. In doing so, we may be on the brink of unlocking some of the greatest secrets of the universe, perhaps even finding answers to questions that have eluded humanity for millennia. As we look to the future, the study of black holes promises not only to illuminate the most mysterious aspects of the universe but also to push the boundaries of human knowledge and technological capability. The quest to fully understand these cosmic phenomena could lead to revolutionary breakthroughs in multiple scientific fields, from fundamental physics to astrophysics and beyond. Moreover, as our understanding deepens, we may uncover connections between black holes and other extreme objects in the cosmos, such as neutron stars and white holes, expanding our knowledge of the universe in ways we can hardly imagine. The path forward is fraught with challenges. As we attempt to peer deeper into the heart of black holes, we will face technological and conceptual hurdles that require creativity, persistence, and collaboration. However, the potential rewards are immense. Black holes are not just distant, incomprehensible objects. They may hold the answers to some of the most profound questions about the nature of reality itself. What happens inside a black hole? Can they serve as bridges to other parts of the universe, or even other universes? Are they truly the endpoints of stars, or do they mark a new chapter in the life of matter and energy? These questions, once considered purely speculative, are now being actively explored by scientists using increasingly sophisticated tools. The rise of new technologies, like the advancement of quantum computers, could also play a critical role in solving the riddles surrounding black holes. With their ability to process vast amounts of data and simulate complex systems, quantum computers may offer new ways of modeling the behavior of spacetime at its most extreme. Similarly, the development of more sensitive detectors, such as the next-generation LIGO and Virgo observatories, could open up new frontiers in gravitational wave astronomy, providing an unprecedented view of the most violent and energetic events in the cosmos. In the coming decades, we may see the discovery of even more exotic phenomena related to black holes, such as Hawking radiation, quantum effects at the event horizon, or perhaps even the detection of wormholes, if they exist. As we continue to push the limits of our knowledge, we will need to consider the broader implications of our discoveries. What does the study of black holes tell us about the universe's past, present, and future? How does it shape our understanding of time, space, and the very fabric of reality? And what are the ethical considerations as we explore these uncharted territories? These questions, though speculative, will undoubtedly form an essential part of the conversation as we continue to probe the mysteries of the universe. The future of black hole research is bright, with many challenges and opportunities awaiting us. As we advance our observational and theoretical techniques, we will undoubtedly make discoveries that challenge our deepest assumptions about the universe. And, in doing so, we may unlock some of the greatest mysteries of existence, bringing us closer to understanding not only black holes but the fundamental laws that govern the cosmos itself. The pursuit of knowledge about black holes is not just about answering academic questions, it is about expanding the boundaries of human curiosity, about understanding our place in the vast, incomprehensible universe. It is a journey that will inspire generations to come, and in the end, it may change the way we view reality itself.